I think we should start. So I'd like to thank everyone for joining us. We're in for a treat today. We have an incredible presenter. First, I'd like to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. The Temerty Center for AI Research and Education in Medicine, or T-CAIREM, at the University of Toronto, has been made possible by the generous donation of the Temerty family. T-CAIREM is an interdepartmental center that serves as a focal point for collaboration among healthcare providers, trainees, researchers, computer scientists, engineers, and industry to advance health through artificial intelligence. Our goal is to transform healthcare through AI. I'd like to quickly mention that the event is CPD accredited. So to obtain your CPD credit, please complete the evaluation form that we'll email to all the attendees following the event. And don't forget to provide your name and email address on the evaluation form. Just a note to the attendees, please use the question and answer function in Zoom to submit your questions to Dr. Doshi-Velez. She will address them during the discussion portion of this webinar, and I will be monitoring them, so don't be shy. We also have a live Twitter feed, so you can follow along and respond to what's going on. Be sure to follow the hashtag Temerty Center Speaker Series. Now, I'd like to welcome Dr. Finale Doshi-Velez. She is she's the Gordon McKay Professor in Computer Science at the Harvard Paulson School of Engineering and Applied Sciences. She completed her MSc at the University of Cambridge as a Marshall Scholar, her PhD from MIT, and her postdoc at Harvard Medical School. Her research interests are at the intersection of machine learning, healthcare, and interpretability. She heads the Data to Actionable Knowledge, or DtAK group at Harvard Computer Science, which uses probabilistic methods to address many decision-making scenarios involving humans and AI. The group works to expand the group's work expands specific application domains, health and wellness, as well as broader socio-technical questions around human-AI interaction, AI accountability, and responsible and effective AI regulation. Really, really honored and privileged to introduce Dr. Doshi-Velez, who has really kindly agreed to speak with us and give her insights on an incredibly important topic in machine learning and AI reinforcement learning. So I'll hand it over to you. Thank you.
Awesome. Thanks so much for having me and for the introduction. I'll just emphasize one point, which is about asking questions. We're all zoomed out. It's been a long time of remote presentation, so please send your questions. Really, the reason why this is a live presentation is for me to be able to answer what's on your minds. So I really welcome any questions that people have. All right, so there's a little, basic background here, in terms of RL and healthcare, AI and healthcare, that I feel like is probably fairly obvious to everyone in the crowd. There's a lot of opportunities when it comes to what AI can do in the health space. We have a lot of, especially now, I don't think we need to justify the fact that health is important, public health is important, and perhaps AI has a role to play. And I also don't think I need to really spend much time talking about why, algorithms can go wrong, work out of all sorts of places, including Toronto has shown that, issues come up in healthcare situations when you start putting AIs into practice, right? So the goal of this talk is to focus on situations where a series of decisions need to be made, which is reinforcement learning, and talking about, first of all, what is RL, where can it be used, how can it be used, but also this important question of how do we validate something that comes out of an RL algorithm. And RL validation tends to be a bit more tricky than just normal AI or machine learning validation. And what I'm hoping is that we leave today with at least the sorts of questions to be asking, even though you may or may not know all the technical ways of solving them. At least we're asking the right questions. So first I wanted to start out with when is reinforcement learning or when is sequential decision making useful? And emphasize that not always, right? There are some healthcare problems, many healthcare problems that are effectively one-off decisions. It can be a question of, does this image have a tumor in it? Will this depression med work? And in these cases, there's not a sequential decision-making problem. We make a decision and effectively we get some sort of consequence, hopefully a good one, from that decision that we've made. Other cases involve, however, reasoning about a series of decisions. So one area we've worked in is in HIV, and there you want to be choosing the meds so that you prevent drug resistance from happening. You're alternating them at appropriate time intervals. You're sequencing them so you don't pull out the big guns first and then get a lot of cross resistance and then ruin your ability to manage the disease later. So there's a long-term effects of your actions that are going on. And similarly, in the running example I'll be using today is a case where we're looking at certain interventions in the ICU where there may be long-term effects, again, from certain decisions that are made. And reinforcement learning is that part of machine learning that likes to, or that thinks carefully about how sequential decisions are made. So here's the obligatory what is RL slide. You may have seen versions of it, but I think it's important just to ground where we are. So here we have the agent, that's the AI system, whatever it is, and it takes actions that go into the world. And the world I'm drawing is kind of a black box, a blue box. The action might be a recommendation, like I recommend that you give a patient this drug. The action might be something more direct, like changing a ventilator setting. And then out comes some observations, some measurements, and some rewards. And that goes into the agent. And we have control over what goes on inside the agent. So we can usually that's divided into two pieces. Usually the agent has some notion of what's going on right now, which we call the state, and how states evolve, some model or some notion of how things might happen in the future. It's not sufficient to just know about what's happening now to select the action. We also need to kind of think about how things might change in future from the now that we're at. So this is, again, very high level picture, but we'll be coming back to this idea and keeping in mind that all of this lives inside the agent, right? This is not necessarily a reflection of what's actually happening in the world, but it's a convenient fiction. And for those of you who are coming from the clinical side of things, I'm hoping that this also makes sense. We have abstractions of how the body works, which are good enough for making decisions, even though they're not exactly, modeling all the details of every chemistry, biochemistry that's going on inside a human being. So how do people actually go about solving these problems? Well, there's two major styles of approaches that I feel like have been useful in the health space specifically. One is the model-based style, where we explicitly think about the future. So if we're thinking about HIV, for example, we might think that there's some hidden patient state that represents the state of their disease at the moment. We have measurements like CD4s, viral loads, mutations, and then our drugs change the state of the patient, which change the measurements that we observe. And we kind of really are thinking about this from sort of a simplified but mechanistic perspective of what's happening. In contrast, another approach could be a neighbor-based approach. And you think to yourself, okay, a patient comes into your office, you ask them about their current status and their history, and you think, oh, I've seen patients like this before. And when patients like this are given this treatment, things tend to go pretty well. Maybe it's from your personal experience, maybe it's from talking to colleagues, et cetera. And in machine learning, this can be formalized as saying that here's your patient in some abstract patient space. Look at all the nearby patients and see what worked for them. Like different patients may have tried different treatments, see which one of the treatments was the most successful on average. And that is not explicitly creating a model, but there's kind of an implicit notion because you're looking at those past patients, their futures, what happened when the treatment was given. So in our work, one of the principles that we have leveraged is these two ideas have complementary strengths. So there might be patients, if you're lucky, honestly, if you're lucky enough to have patients that look just like you, then medicine is so complicated. Probably the best way to make a decision is to look at your neighbors and make a decision based off of what was best for your neighbors. Even when you're making a long-term decision, when you have enough data, you can see those long-term outcomes based off of what has happened to past patients. On the other hand, if you might be unlucky. So you might be this green patient over here who has no neighbors. And rather than say, well, I'm going to model this green patient based off of these blue patients that are kind of far away, it may be better to fall back on a simplified mechanistic model of how disease evolution occurs. So our idea, several years ago, we had this insight. We were like, why don't we combine these two things together and create a reinforcement learning algorithm that is able to take advantage of both of these scenarios appropriately and switch between them. And so we did. And I'm going to tell you an example of one of those cases, which involved managing hypotension in the ICU. So here, in terms of how to set up an RL problem, our goal was to reduce mortality for patients with sepsis, and how the actions that were available were better fluid and vasopressor choices. These choices have some long-term implications, so it's a sequential problem. Therefore, we were using reinforcement learning. And just to formalize things a bit more, the data were a cohort of about 15,000 patients with sepsis from the MIMIC data set, using similar cohorts that other people had published with before. And then we had to define the state. So remember that notion of like, what does the patient look like now? Right? The agent needs to have that notion formalized for any sort of reinforcement learning problem. And to do this, we wanted to keep track of the entire history. We didn't want to just look at the current set of measurements. So what we did is we used an RNN, a recurrent neural network, with 128 hidden units to take the entire history of the patient and compress it into those 128 numbers. And that was the state of the patient. The RNN was trying to collapse everything about the past that was useful for predicting things about the future measurements of the patient. Then we had to decide what's our action space, like 3 key things in reinforcement learning are states, actions, and rewards. So we defined what state means, or how we're going to summarize what a patient's condition is. Then we have to choose what are our menu of options or actions. And there we decided to discretize vasopressor and fluid doses into 5 levels, 0 and then varying dose interval ranges. And then we had to decide on the immediate reward, right? Because in reinforcement learning, there's a long-term goal, which is to maximize a cumulative sum of rewards. But we have to decide kind of in the moment, how's the agent going to be getting feedback on how it's doing? And we came up with a reward function that had to do with the log odds of the 30-day mortality. And if it looks kind of funky, it is kind of funky. And this is one key point that I'm going to emphasize, is that crafting reward functions is a very delicate art when it comes to RL. We chat with our clinical colleagues and we're like, hey, if we design the function this way, then we learn a policy that looks like this. If we design the function this other way, it looks like that. And there's a bit of back and forth to try to figure out what's the right reward function. Because the one thing that's really important to keep in mind is that the agent is going to optimize that reward function. It's going to optimize the heck out of that reward function. So whatever weirdnesses you have in that function, it's going to try to take advantage of them. So designing the function is a really important piece. Anyway, so we did all this. And then we got some numbers. And I'll talk a little bit about these numbers later in the talk in terms of what they are and how they came to be. But first of all, we had ways of estimating the quality of the policy if it was just a physician quality and physician behavior. By the way, non-recurrent is if you use just the most recent data. Recurrent is if we use that RNN to include the past data. And so we have the physician. The kernel is the neighbor-based approach. DQN you can think of as a model type approach. It's a value-based method. If you don't know what it is, that's fine. If you do know what it is, that's also great. And then here were our mixtures of experts that were combining this neighbor-based approach and a model-based approach and trying to take the best decisions. What you see is that especially with our recurrent state encoding that included the past, we're getting numbers that look quite a bit better than our physician numbers. And so that looked good. And then we took a look just in terms of the plots, and we looked at for fluids and vasopressors. Let's say you deviate from what our recommendation is. So 0 means 0 deviation from our recommendation. And as we look at all the data points we have for every patient, we see, what was actually done and what we would have recommended. And we can compute the deviation, and we can compute mortality rates based off of the deviation. And it looks like when clinicians didn't happen to deviate, they did mortality rates were the lowest. So again, looked great. We were happy. This was part of a class that I was teaching in 2017. And while debugging, one of the students decided to just, try to plug in a random policy, just to, they're just trying to get the thing to plot, right? And this is what we got. So what we're seeing here is that we know that so in red, for example, here is the optimal policy. This is the policy that we learned, doing that model previously, that state space, that reward function, blah, blah, blah. And then the random policy doesn't consider the reward at all. It just says take random action. We know that's a bad idea, right? And we see that it has a very similar shape. And this was like this is embarrassing. It doesn't mean that our optimal policy is bad, but what it's showing is that this measure is not able to tell the difference between something that's clearly good and clearly bad and something that's maybe good. And the reason it turns out to be the case for this is that there's a lot of data kind of sitting around here because there's a lot of no actions, and no actions get recommended a lot. And when actions are recommended, and there's some more deviation possible in terms of the exact amount of dose or something like that, that's usually when there's something wrong with the patient. So in general, when actions are happening, there's more chance for deviation, and there's also more chance for mortality. So that's kind of why we see this curve. But for us, it was really kind of this warning bell of like, so far we've been doing things kind of the normal RL way. You set up your state space, you choose your actions, you choose your rewards, you do some optimization, you do some off-policy evaluation, you get some numbers, and you're done. But clearly you are not done. And so what I'd really like to emphasize for this talk is that this issue is just one example. All stats have issues. As we've been working in this space, and I'm sure many of you also have similar experiences, there's weird data processing errors. We once were looking at a data set where somehow T02 turned into T0, and suddenly it looked like loads of patients had cancer. We've learned non-causal models, we've fit to confounders, and avoiding all these pitfalls is really hard, and particularly hard when it comes to reinforcement learning. So what we're going to do for the rest of the talk is to say that in some senses, that initial setup that I talked about was easy. And how do we actually go about validating these RL models? And I'll talk about some of our journey with that original hypotension management problem and tell you where we are today in terms of creating models that are easy to validate. So here's my view of like the overall batch validation roadmap. And when I say batch, I mean, what do you do before you do a prospective study? So this could also be like retrospective validation roadmap. And there's going to be a set of techniques that are more number focused and a set of techniques that are more human focused. So in terms of statistically focused things, there's really basic stuff that one can do. And one thing that I've actually been really excited about is as I've been reviewing papers in machine learning to clinical journals, I've been seeing more and more of these sensitivity and robustness checks. So I feel like overall as a community, we're doing a great job with this. And I'll just provide a couple of examples of reminders of what this sort of thing looks like. So a basic question in terms of robustness is, does the result replicate across sites and measures? So this is an example from our HIV work, not our work with hypotension management. But when we were checking to see whether our mixture approach was doing better, we checked in two cohorts, the Swiss HIV cohort and the EU resist cohort. And we checked 3 different ways of measuring whether on retrospective data, whether one approach was better or not. And the fact that we got consistent results across 2 cohorts and 3 measures is not conclusive, but if those numbers had been inconclusive, that would have definitely been evidence that maybe something is wrong. Similarly, there are choices of parameters in these off-policy evaluation techniques. And I'll get to what those techniques are in just a few moments. But what we did some really careful, this is in the sepsis space, we did some really careful check of like whenever you need to use control variates, which are basically the numbers that you use to decrease the variance in a statistical estimator. If you choose different choices of control variates, different ways of reducing the variance, do you get a consistent set of results? And I'm not going to interpret these plots, but I'm just showing that, you know, we didn't just do those numbers that I initially showed you before. We did a lot of homework to try to check whether those results were valid or not. Right. So there's a bunch of the really basic stuff that one can do, like those things. And then there's kind of more the usual, I would say, which is off-policy evaluation. So I'm going to briefly summarize, you know, how that works, just to give you, again, a menu of different approaches, the quantitative approaches to checking whether you have good methods. So in terms of off-policy evaluation, the core question, and then or retrospective checking, because you really will need to do as much retrospective. Maybe this is obvious, but I just want to emphasize, when you're learning some policy, some new treatment policy, especially in the RL case, where it's saying, well, you do this action, and 10 hours later, 2 years later, there's going to be these long-term benefits from these choices of actions. We know how easy it is for one-off models to get confused. Now there's a whole sequence of decisions and whole sequence of places where errors can compound and things can be extrapolated. So we want to be really careful in terms of what's going on there. So we want to do as much checking as possible before anything is put out there in the world. I see a raised hand. Mohsen, do you want to ask your question? Are you able to ask questions? And then January. I'm not quite sure how this works. Are you all able to just unmute and ask? Ah, okay. You have to put questions into the Q&A, Roger. Okay. So folks who raised hands, do you want to type in your question into the Q&A and I will answer it there.
Exactly. If anyone has any questions currently, please put them in the Q&A box or in the chat box as well. I'll check those too, but Q&A would be great. And if you can wait, we'll take them afterwards.
Okay, so while folks are typing, I'll keep talking. But as soon as questions come in, I'll switch over and answer for you. Okay, so the question is, do better control variates correspond to better policies? No. So control variates are actually let me click through two more slides and I'll tell you exactly where they kind of fit in. So the question that we're often trying to solve, or the question that we're trying to solve here, is that we see the behavior pi b of what the clinician was doing. And then the question that we have is, how would some other policy, pi e or pi evaluation proposed by the agent perform? And there's two major classes of ways of attacking this problem. One is via importance sampling, which is to say that we're going to weigh the trajectories based on how likely they were under our evaluation policy. So if something was very likely to be performed by our agent, then weight that trajectory, say this yellow one, higher. Whereas if the probability under pi e, our proposed policy of this set of actions, was relatively small, then weigh it down, right? So again, from a high level perspective, what importance sampling is doing is picking out the trajectories that amongst all the trajectories that the clinician already performed, pick out the ones that we would have done or the agent would have done and weigh those up and average them. And then what a control variate does is so the issue with this importance sampling based approach is variance. What if there's only a few patient trajectories that have our recommended action? So we can have a data set with 15,000 patients, but only end up with 5 trajectories or something like this. And this is why it's really important to look at the effective sample sizes in papers that correspond to what our agent would have done. And then what a control variate does is it tries to reduce this variance. So it's the variance of the estimation of the quality of the trajectory. It doesn't change the quality of the trajectory itself, the quality, of this evaluation policy, but it tries to change the quality of the estimate of how well we have characterized the quality. And the way it does that is it tries to subtract off a guess of how well we think the policy is doing. So doubly robust methods are one example of this particular category of statistical techniques that people can look at in more detail if you're curious. And basically, the other major approach to doing this is that you take all the data, you build a model, and once you built a model, you can simulate however any policy, right? Any treatment policy. So that you use the data, build a model, treatment policy, you can simulate outcomes. But the problem with this is bias. If the model is off, if you built this model poorly, the results will be off because you're dependent on this data. You're not directly using the data to make an estimate. You're using the data to make a model first. And what these doubly robust methods do is basically say if one of these is good, right? If you've got good importance sampling or you've got a good model, you'll still work well. And so the control variates have to do with adding in this guess and combining your model-based guess with your importance sampling-based guess. So I don't feel like I have the time to go into, or this is not quite the place to whiteboard it out, but it's a really good question, and there's some really, really exciting work that has been done in this area in terms of many recent advances. But the intuitions are the same. You're either trying to build models that have bias, or you're trying to average over existing trajectories, and those have variance. And somehow, and again, many methods try to combine those two trade-offs together. So those are mathematical methods, right? Quantitative methods. And I like to just emphasize that these have strong limitations. They make assumptions about the fact you truly have a state space. Did you have all the relevant features? And in health settings, the answer is no, right? We know this. We don't measure everything that's relevant. So we know that we're missing a lot of things when we try to train our machines. We don't even know exactly how to quantify the reward function. So there's some major limitations to these quantitative approaches. Not to say that you shouldn't do them, right? It's absolutely essential that you do them, because if they come out badly, again, that's a red flag. But if they come out well, then maybe that doesn't necessarily mean that you've got, the brand new cure, the panacea to solve whatever problem that you're trying to solve. And that's why, in terms of validation, we need both, right? It's not one or the other, but we need ways for humans to also inspect what's going on and see what's going on. So one way to do that would be to look at specific decisions. So that's what I mean in terms of locally. And we've done this. So for example, with HIV, we checked against standard of care. We asked the panel of experts, do you agree with these decisions that are being made by the agent at certain points in time? And the concern that you kind of get to is how do you know that you've checked enough examples? How do you know that something's not hiding somewhere? And so that really leads us to the question of global validation. And recently, we had a CAI paper where we were presenting a local model, this was in a psychiatry case, where we had an interface and we were asking primary care clinicians how they would interact with this interface for antidepressant recommendations. And everyone just assumed that it was going to work perfectly, that all the recommendations were good. And so during the interviews that we were having, at some point we asked, do you question, do you think that something might be funny here? And they were like, well, why would the hospital have bought this if it wasn't good? Right? So just emphasis, and it's fair point, right? Why, these people are busy, they're going through their day very fast. They're not going to want to be checking each decision one at a time, at the bedside. And so doing some global validation of the model is really essential. But how do we go about doing this? So one option is to just show a lot of examples. And we've done an experiment along these lines. These are toy examples where we said, okay, here is a grid, and you see actions for some of the things on the grid. And then based off these examples, can you extrapolate? Can you tell us what's going to happen at other locations in the grid? And folks can take 2 seconds, 5 seconds to imagine for themselves, like, what would you do, for example, in this box right over here? And then we asked a different question. I'll get back to that grid world in just a moment. But of a similar vein. So we said, here are various measurements for a patient with HIV. This is using the baby HIV, baby meaning like very toy, not small child. The toy HIV simulator that's out there, 6 variables, super simple. We use that simulator to generate trajectories, and we said, okay, here's the sorts of actions that the agent is taking in various situations. Here's your quiz question, right? Similar to before, here's your quiz question, what happens when the agent is here? Here's your quiz question, what does the agent do in this particular location? And the idea being that if people can look at a couple of examples and say what the agent would do in another set of examples, and maybe that's great, right? Maybe that means that they understand the system and then can point out whether there are issues. Well, what we found is that people use very different methods of extrapolation in these 2 different scenarios. In a grid world, people were more often assuming a goal. So IRL is inverse reinforcement learning. So they kind of assumed that the agent, was trying to reach the blue squares, for example, because in blue settings, oftentimes the agent is stopped, and arrows are often pointing in blue directions, which is true. So they assumed that there was some goal-directed behavior going on, and they guessed actions based off of the goal, or were non-specific, right? This is really important. People described their approach, and we could not tell what they were, whether it was an imitation learning or a inverse RL. So this is copying actions. This is goal-directed behavior. In the HIV scenario, like, we have no idea what the goal is. If it's trying to get these markers to a certain location, it's really not obvious. If you are asked this quiz question, I just look and see, like, what's the nearest, maybe it looks like this one, I guess treatment B or something like that. And I just copy. And we noticed that people were mostly copying. And why is this a problem, right? Why am I spending time on this? Well, I'm spending time on this because this is just pointing out that when we provide examples, and different people, notice it's not the same even for each domain. Different people are extrapolating in different ways. And so it's not really a great way to check, or it can be a partial check. All of these things are partial checks, but we have to have this caution that we don't actually know, just because people saw these examples, do they really grok the system? Rather, we know they don't truly grok the system because they're extrapolating in different ways. So that brings us to the final segment, which is, can we, by rules, or can we just make the models inspectable? And Cynthia Rudin has been a strong proponent of this for many years now, where, especially in something high stakes like healthcare and decision-making in those sorts of scenarios, it should be really clear what's going on, as clear as possible. And with some effort, it should be possible to design these decision-making systems, even in RL settings, such that people can truly just inspect the whole thing. And that has really been the quest in our lab ever since that initial case, where that first model I described to you, recall, it had 128 continuous variables, hidden variables in that recurrent neural network. Did we really need that many hidden variables? It was the question. I mean, it worked for some definition of work. All the statistical tests looked very decent, right? But there was no way for us to really inspect that model to see, is it doing anything sensible? Is it missing some confounder, or is it taking advantage of some confounder in an inappropriate way? So the idea that we had was, let us start with a generative model. These are models where diseases create the data, but let us train it so that it's useful for decision making. So idea here could be, here's the patient disease state. Patient disease state could be super complicated. We could have stuck in 128 continuous numbers inside each one of these bubbles. But what happens if we make it small, like real small, like 5 possibilities small? And the reason why we thought that this might be plausible is that in our heads, we're thinking that clinicians probably are not reasoning, or they're certainly not explicitly reasoning in such a high dimensional space. They probably have categories of patients kind of as they see them, and they're choosing actions based off of those categories. So it's not an exact witness, but we kind of have a sense that, hey, this problem there might be a simplification of this problem that actually performs reasonably well. So going back to that hypotension management problem, we looked at, we looked at all, we just focused on hypotension, whether or not they had sepsis. That was not a particular inclusion criteria. The inputs or the states were a bit smaller, 9 vitals and labs over 72 hours. The actions were, again, these discretized fluid and vasopressor administrations. Because this work has happened over several years, our reward functions are also changing. So things are not exactly comparable, but the story that I'm trying to tell is the story of increasing interpretability. But here our goal was to just keep the blood pressure in a certain range. And that's a more near-term goal, right? Rather than reducing mortality. And the idea there was that maybe this is a more robust thing to optimize. And then the approach that we took was to learn a small discrete POMDP, or partially observable Markov decision process, to recommend actions. And the way we were going to do this is our objective function was going to say that we want to maximize the log likelihood of the data with respect to the model. So M is the model. So we want this little model, tiny baby model that we're going to learn. We want that model to explain the measurements that we've seen as well as it can, right? That's the first term over here. And here's our trade-off parameter, lambda. We wanted to have a great off-policy estimate. So once you use this model over here to solve for the best set of actions to take, we want that to, we're going to take that's our pi star with respect to M. We're going to estimate its value using those estimators that I talked about before, and we use an import and sampling based estimator based off of the real data. So we can't hallucinate. We can't create a model that'll let us cheat, because if the model tells us to do terrible things, our off-policy estimate will be terrible. And we're going to try to trade off these two things, right? Explain the data and find a good policy, right? And here are an initial set of results. So what we find over here is that if we only try to optimize the value over here of this model, it's wrong direction, that gives us this point over here. So this axis is estimated policy value. This axis over here is how well we explain the data. We want to be in this corner where the smiley face is. If we try to learn a great model, the trouble is that a model that explains the data might not be the best for planning, because there might be major things going on with the patients that are not even related to their hypotension, right? They have a respiratory issue and they're on a ventilator, and that's like a big signal that all of a sudden a bunch of numbers change. And some of that might be relevant to hypotension management, but maybe not all of it. They have a kidney failure. And they're on dialysis, and that's a big shock on the system. And if we only have 5 states, right, where we're making this really tiny, do we want to use our 5 states to talk about kidneys and respiratory issues, or should those 5 states really focus on things relevant more to circulatory issues around hypotension management? And the key point here is that we didn't want to go in and say, oh, we're going to create specific hypotension relevant states, because we didn't know what they were. But we were saying, learn a model such that you can make good hypotension recommendations. And in doing so, hopefully those 5 states that you learn are going to be, hypotension relevant. Yeah. And so here our approach is over here, where we're explaining the data not about as well, and depending on that trade-off parameter, as the model that just focuses on explaining data. But we're the places where we make trade-offs, where we do worse, it gives us significant benefits moving upward in terms of policy estimation, policy performance. So that's the quantitative part. But then in terms of the qualitative part, we can create plots of different action choices, and have our colleagues look at these and try to analyze them. This still looks a bit confusing though, right? So we were, on one hand, we were very happy that we distilled it down to just 5 states, and we can plot values of various measurements across these 5 states to try to get people to think about what they are. But it's still kind of a slide full. So kind of even more recently, next step was, can we make this even smaller? Because 5 discrete, hidden discrete states is still kind of a lot. So our most recent work in this space has the following flavor, where we try to take advantage of the fact that there are only a few situations where we can make any recommendations whatsoever. In particular, if we look at these colored blocks and we consider them to be different states, every time we're in light blue, the clinician action is A1 in this little toy example. There is nothing to learn here, right? There is no way that a statistical technique, a machine learning technique, could estimate what if we did A2 instead, right? It's just impossible. We can't ask the impossible, right, of our tools. So the only places where the doctors disagree in this toy example are in the red and the yellow situations, because sometimes there's A1 and A2, and sometimes there's A1 and A2 over here. And so just with the 2 states to optimize, we can build a really tiny model, right? Because the rest of it can be marginalized out from a statistical perspective. And we just look at the cases, these forks in the road where clinicians disagree. And by focusing only on the forks in the road, we create an even smaller model that is more inspectable. So we have this. We applied it to the same hypotension management problem, and basically ended up with 14 situations, decision regions, where clinicians disagree on what action to take. And we could describe all 14 regions in one picture based off of the features that went in. And again, it's like kind of it's not the most pretty picture, but it is one picture, right? That a clinical expert, we sat down with Leo on a phone call, and we looked at the different numbers here to try to see, does this make any sense? Like, does this mean that we're missing some variables, right? Like if we see a patient that looks like this, what is actually going on with that patient, right? That in terms of things that are unmeasured. We were able to have those conversations, which we hadn't been able to have with the previous 2 cases. The other thing that we were able to do is that, okay, there's only 14 cases. Here's the behavior policy. We split this time only into 4 different treatment options, nothing, fluids, vasopressors, both. And this is the probability of each choice. And note that in each of these columns over here, in terms of clinician behavior, there's some confusions or a disagreement. That was the whole point. We're finding places where clinicians disagree on what to do. And because this is so tiny, 14 places, 4 actions, we were actually able to plot 4 different reward functions. So this is not the greatest titling, but the piecewise policy is the policy that looks at just keeping blood pressures in range. Mortality-based policy looks at doing something kind of like that first version where we were trying to manage odds of mortality. And the terminal policy also is looking at mortality, but calculated in a different way. Great. So there's a question here saying, how do we determine physician disagreement? So this is a somewhat subtle issue. And the way we go about doing this is we define a state space. So the exact way that we do it is we try to define a state space so that we can predict the action that's going to be taken as well as possible. So we try to maximize we try to create a representation that allows us to guess the action that's going to be taken the best that we can. And then we look for situations where we just are not able to guess, that the quality of our guesses are poor. And so there might be a particular configuration over here, for example, of mean arterial blood pressure, lactate, et cetera. And in this situation, when patients had values like these in the data set, we notice different actions being taken. And important note is that those different actions could have been because people just have different ways. Some clinicians are more aggressive in their treatment, some are more conservative in their treatment. But it could also be the case that there was a missing confounder. And the whole point of this was to be able to have that, not to say that we had the correct answer, but to have that conversation. Yes, and it could absolutely be influenced by patient goals. So that's another example of a confounder that could be there, and kind of hypothesis being that someone wants to get really aggressive treatment, and maybe someone else, based on their condition, it declines that particular option in the ICU, and this would apply in general as well. So this to me is just really exciting that we took a problem that had 128 hidden variables. It was just completely non-inspectable and didn't allow for important forms of validation. And then roughly 4 years later, as we've iterated through different approaches, we get something that's much smaller. We're not saying it's correct yet, but at least it's much more checkable. And so as we kind of go through this and we check with our colleagues, do these things make sense? We feel like we're getting to a point where we can actually feel good about maybe making some actual clinical recommendations based off of these RL algorithms that we are using. So that is like the batch validation roadmap, and really emphasizing that there's important numbers that obviously have to be computed when it comes to sensitivity, robustness, OPE. If something's wrong there, if those numbers are off, then you have a real problem. But if those numbers look good, really want to emphasize in terms of takeaways, this last option, this like being able to inspect the global model by rules. I and other researchers are doing a lot of work to try to make these models inspectable. And I feel like especially for high stakes decision-making scenarios, we almost need to demand this so that we can be able to check the models for things like the patient preferences or the confounders or other forms of missing information that might be skewing our results. Of course, batch validation is just one piece. We build the system. That's where we started this talk. We do the validation. That was the second half of this talk. And then there's many steps in terms of doing silent trials where the tool is not being used, but it's kind of live and we're watching what it's doing actual clinical trials, putting it out into the world, and continuous monitoring. So what we talked about today were really just what I see is the first two steps in the context of reinforcement learning of how you get tools out there for real healthcare situations. So just to conclude, and then I'll take more questions, RL in health has a lot of potential, but careful validation is really important. It's always important, but in RL, it's particularly subtle. And we want to be able to check for all of these things. And today we got a taste of how to formulate a problem, how to set up those states, those actions, and those rewards, and then laid out a roadmap for how to do validation in those settings, retrospective validation in those settings. And then going forward, especially for those of you who are coming from a more clinical background or statistical background, trust your training. All of those things about replication and sample size, confounding, all those things still hold in RL. And engaging with human experts with the requisite clinical knowledge is super important as well. And then just noticing that it's really important to engage also, if you're on the clinical side, with AI experts on more subtle points, because one thing has just become really clear to me over the last 4 or 5 years that we've been working on this particular set of problems is that we just understand more and more the ways in which, while these methods have a ton of promise, I think there's also a lot of ways it can be tricked, and going through those checklists is obviously really important to create something that's responsible and effective. So I'll leave with that and take questions.
Great, thank you so much. That was a terrific presentation. There is another question, and it can be a little bit more, I guess, involved when you think about different players wanting different things. So there can be different decisions that could be made depending on the goals of treatment. So for example, a patient may have a different goal than a clinician would. So and I imagine with reinforcement learning, there's one reward function, or there's one kind of end goal that you get at. Are there ways of incorporating multiple perspectives on what success would look like?
So I think especially with these smaller models, we are able to show a range of possibilities. So this is work that is ongoing work, so I don't have results yet, where we are trying to identify ways to solve robustly in these sorts of ways for multiple different options. And in general, that is an area of reinforcement learning, like multi-objective reinforcement learning, that allows you to find policies for a number of different weighings of different preferences. So I think that is it, from a technical perspective. There's great work that has been done and that is happening to try to get that kind of bridged over to this space. And then I think there's also the question of like, how then do you let the clinician and the patient have a conversation about those? So in the one-off setting, that's something that we are working on in the context of like antidepressants, where you might come to some shared consensus around, what am I okay getting fat, or am I okay not sleeping? Like all of these sorts of, can I manage to take a drug 3 times a day, or do I have, do I need a drug that can only be given once a day, because I'm never going to take something that's, needed to be taken 3 times a day. And having it as a conversation. I would hope that it's a conversation. That's kind of the standpoint that we're coming at it from. If there's a setting where, they're truly at odds, that's not something that we really thought about.
No, great, thank you. There's another question around any insight on how recent breakthroughs in deep multi-agent reinforcement learning can be applied to solve large-scale problems in healthcare.
Yeah, so Aaron, I'm wondering if you, and this is like kind of the tricky thing with doing things over Q&A, I'm wondering if you can expand on like, who are the multiple agents? Are they different parts of the health system, or are they different parts of like modeling different organ systems, or kind of what you mean by that? Maybe we'll go to the next question and come back to that one.
Yeah, that'd be great.
Yeah. So the next question is, how would you incorporate clinician skill and expertise in the qualitative evaluation? So yeah, I mean, the qualitative evaluation exactly for that. So when we showed, for example, plots like these, so we had the policy recommendations, and we had this sort of picture, and we had an hour-long phone call with Leo, who I think was on your series a little while ago or earlier. And we said, in this situation, let's say decision region 3, what does this mean, right? Like if you see a patient with these scores, what does that mean to you, right? Like, what are you imagining? And would it make sense to do nothing? Because like we're consistently doing nothing, but in practice, we're seeing a combination of do nothing and vasopressors. Like, does that make sense to you? Does it make sense to you that clinicians would do those 2 different things, and yet our agent recommends always doing nothing between those 2 forks in the road? So that's a very concrete example of incorporating clinician skill and expertise, because then you're able to say, oh, is this an issue of just like, the younger ones are gung-ho and they want to just try everything, and the older ones are like, okay, the body just needs time to heal. If it's going to heal, then we don't want to muck with adding additional strain on, etc. So that's a concrete example of this sort of thing. So we're not and then that gets looped in, right? We get feedback. So for example, in this case, for those of you who know things about hypotension management, we'll be like, why are there mean arterial pressures over 65 here as the average, right? So then that was one place where we kind of went back and we're like, okay, initially we didn't trim our state space in a certain way, but if we're really focusing on fluids given for hypotension management, then maybe our state space was also incorrectly defined, and that's where we're reiterating exactly now as we speak.
Great, thank you. Yeah. And I'm going to take the prerogative of asking the final question.
Sure.
Explainability. It's tough on some basic machine learning models, let alone reinforcement learning. There's a lot of debate around the beauty around machine learning approaches is around all the complex relationships that are just so hard to explain, and giving a prediction based on those. I think some of the things people talk about is in a modern complex medical decision, there's about 1,000 parameters you need to take into consideration, where humans can only process 7 plus or minus 2 things at the same time. How do you deal with explainability in the context of reinforcement learning, which is another level up? Can you give some guidance and recommendations around that, or should we just not even try and tackle explainability?
No, explainability is absolutely essential. And I'm going to answer your question, and I see Aaron reposted his question, so I will answer that one as well. So briefly for Aaron's question, I definitely see situations with multiple decision makers being beneficial. I'll give a concrete example that we're thinking about now that maybe fits what you're thinking about, where we're thinking of, we're in the mobile health space. You can have agents that help optimize for different parts of someone's sleep hygiene. So it's the same environment. You're trying to manage someone's sleep better, but different agents are kind of focused on different parts of it. And then there's like a meta agent who's kind of making sure that all the sleep hygiene agents, the red light filter agent and the caffeine agents and et cetera agent are not bugging someone at the exact same time, which would be seriously annoying. So there's absolutely those scenarios. And then to your question about explainability. So this is what we're trying to get to in some of our work here and that going forward, where we talk to each other about how we think things are going to happen in future. For example, like, if we go with this option, we believe that someone's going to have these better outcomes, but maybe this other risk that they are getting. Whereas if we go with this other scenario, so other things might happen. And what I think AIs and machine learning tools are really good at, if properly designed, is that they can help kind of you navigate the probabilities of all those different trajectories in terms of what might happen. Because people are notoriously bad with even single probabilities. You have layered probabilities, which is really not good at calculating those risks and really calibrating them. But at the same time, a lot of things can be abstracted. And part of our quest for small models is exactly to make stuff more interpretable and inspectable, because those insights are essential. If you have systems that just, there's a really clear reward function and it's a closed system, then maybe you don't need explainability. But in the health space, I just don't see that happening. There's too many interests. The clinicians, the patients have needs that they can't quite express, and they're going to need to be able to twiddle the system, as we just talked about, to get to those needs. Not everything is being measured. There's going to be information missing. So it is doable, right? My thing would be, if someone says that it's impossible, then that's BS. You should not accept that. We actually need explainability as one of those key pieces for validation.
Oh, that's great. Thank you so much. And at this point, I know we're at time, so I really, really want to thank you now for a terrific presentation. Really appreciate you sharing your time and knowledge with us. So we're really grateful. Thank you.
Yeah, thank you. Thanks for having me.
Thank you. And for everyone, please keep up to date by following us on Twitter and subscribing to our list on our website, tcairem.utoronto.ca. Thank you very much, everyone, for attending, and we will hope to see you in the next one. Thanks, everyone.